now. All right, welcome everyone to today's Astroparticle seminar, and we're very happy to have Silvia Celli here from Sapienza University in Rome. Silvia did her PhD at the Gran Sasso Science Institute in L'Aquila in Italy. Then she was a postdoc at the Max Planck Institute for Nuclear Physics in Heidelberg. Then she came back to La Sapienza as a postdoc with a L'Oréal UNESCO Fellowship for Women in Science. And she had, if I'm not mistaken, a short stay at the Australian National University. And then she returned to La Sapienza, where she's now a research associate. Silvia works on a number of problems in high-energy astrophysical sources related to particle acceleration and escape, and the connection between neutrino emission and gamma ray emission and cosmic ray emission, and in particular, the dynamics of supernova remnants and gamma ray bursts. And she's a member of Antares and Chem3Net, the two neutrino detectors in the Mediterranean Sea, and of CTA, the gamma ray ground array in planning and construction. Today, we're happy to have her talk to us about supernova remnants, cosmic ray escape, and radiative signature. So, Silvia, thank you.
Okay, thank you very much for the invitation and the nice introduction. So the topic I will discuss today, as Mauricio introduced, is about supernova remnant, and in particular about how cosmic rays are accelerated in these sources and how do they escape the shock, which is the acceleration site, and produce the radiative signature that we are about to that we see. Basically, what I show here in this slide is the measurement of the cosmic ray spectrum that is performed on Earth since more than 100 years. And as you see, the flux, these particles basically are mostly protons. And as you see, the energy dependence of this flux is a rapidly declining function of the energy. Meaning that most of the particles are low energy ones. So the bulk of the energy in cosmic rays is at the GeV energies. You see two important spectral features here in this plot, where basically the trend changes the slope. One is the so-called Ni at about 3 × 10⁻15 electron volts, where the spectrum steepens from an e to the minus 2.7 to an e to the minus 3.1 power law. And then you have we have at about 10 to 18 electron volt a second feature, which is called the Ni, where the spectrum gets back harder. And then you have a sort of high energy suppression, whose origin is still very much debated. What I want to mention here is that if you compute basically the integral of this spectrum, the energy density which is contained in the cosmic rays is of the order of 1 electron volt per cubic centimeter, which is of the same order of the magnetic field energy density and the energy density in thermal radiation, like the cosmic microwave background. Meaning that basically the cosmic rays are particles which might affect the dynamic and the evolution of the galaxy. Well, what I want to discuss today is basically the energy range below the first features, the Ni. Of course, we would like to understand which are the accelerators that are able to describe this kind of spectral trend, spectral intensity. And typically we call this kind of accelerated PeVatrons, because they should be able to reach at least PV energy with a straight power law showing no cutoff in order to explain the cosmic ray observations. The problem with understanding the origin of these cosmic rays is that being electrically charged, they are subject to deviations in magnetic fields, both galactic and extragalactic ones. And so it's not really obvious to point back at the emission sites unless you know very well the distribution of magnetic fields. But an alternative to point to the cosmic ray sources is through the secondary particles that are producing cosmic ray interaction. And for instance, we can adopt gamma ray and neutrino astronomy for these purposes, as I will now explain in a few moments. So just let me give you the broad idea which has arisen since 1934, that the major sources of this cosmic rays up to the Ni, which are the so-called galactic cosmic rays, are remnants of supernova explosion. And this comes as a result of energetic consideration made by Bade and Zwicky. So basically, if you compute, starting from the energy density of the cosmic rays, the power which is contained in this flux of particles, it is of the order of 10% of the power which is continuously injected in the galaxy by a supernova explosion. So this means that if you assume that 10% of the bulk kinetic energy of supernova gets transformed into non-thermal particles, then you can at least reproduce the power observed in cosmic rays. So this was really a very first consideration. And then it was soon understood that the shocks of supernova are ideal acceleration sites. We also have a beautiful theory which is called the diffusive shock acceleration theory that describe how particle gets accelerated at shock, basically charged particle bouncing back and forth of the shock surface, and this would produce a spectrum, a differential energy spectrum of particle, which is a p to the minus 4 power. This reads in the relativistic domain like the e to the minus 2 in the ND energy distribution. So if this, so if protons are accelerated, for instance, at this supernova Remnant shock, then we expect this proton to interact with the target gas density all around and produce in PP collisions charged and neutral pions was decayed and would produce neutrino and gamma rays. These are neutral and stable particles, and so they could they actually point back to the site of the emission. So actually with our Cherenkov telescope, both neutrino, as I show here in the bottom of the slide, and gamma ray instrument, we could be able to see the radiation. We are able to see the radiation from these sources. So there is a stringent connection between gamma ray neutrinos and the primary particles which have emitted them. But the important point is that we would like to unveil the sources of the protons, because most of the cosmic rays are protons. And so we need to look for the so-called hadronic sources. Now, neutrinos are unique signature of the presence of high energy neutrinos are unique signature of the presence of the accelerated protons, because they are only produced in interaction of protons with the target matter field or radiation field. On the other hand, the photons do not, let's say, unambiguously unveil the presence of hadronic accelerator, because they could be produced also in leptonic processes. So leptonic processes are those that involve cosmic ray electrons, which lose energy, for instance, interacting with the matter, radiation, or magnetic fields. So the idea is that the gamma rays are difficult to discriminate in origin, because there are leptonic processes that could produce analogous features in the source spectra. This is something I will now soon describe, showing you a specific case where it is very difficult to understand if the radiation observed is hadronic or leptonic in origin. But first, let me go more in details, also for the students, with respect to the possible hadronic interaction channel where they occur. So you see here, I wrote down the two processes for hadronic production, where you have accelerated protons interacting with matter, or accelerated protons interacting with radiation fields and resonantly producing the delta plus. So in all of these cases, as a result, you will have a production of pi0 and charged pions, which then produce respectively gamma rays and neutrinos. So in PP collision are more likely to occur in a region, in accelerators, there are the so-called cosmic ray reservoir with dense radiation matter field, while P-gamma interaction are more likely to occur where there are dense radiation fields, so like gamma ray bars with jet structure or active galactic nuclei. while the PP collision, for instance, supernova remnants, you have all dense gas target, which could offer the target for this collision. And it is important also, I would like just at the beginning of the talk to give you an idea of the characteristic energy of this secondary particles that are produced. For instance, gamma rays from the pi0 decay would take about 1/10 of the proton energy, while neutrino, each of the neutrinos about 20th of the proton energy. We should not also forget that together with the neutrinos, if muon actually decays, also electrons and positrons are produced, which could provide other kind of signatures for the presence of high energy protons. So let me come to these radiation processes and how typically the spectra of sources are observed, and in particularly, let me focus on the high energy domain. As you see here, for instance, radiation from GeV to TeV as produced in leptonic process like inverse Compton should show a kind of a spectrum which is quite different from the one that one expects from the pi0 decay. So in principle, from spectroscopical studies of sources, even only with radiation, one should be able to discriminate among these two scenarios for the origin of the radiation. But life is not that easy. So let me say that these are two spectra which are obtained, assuming, for instance, here, protons, primary protons and electrons with spectra that are consistent with diffusive shock acceleration, so e to the -2 power law, but this is not necessarily the case. And in particular, let me now give you an insight into one of the highest energy supernova remnant detected in the TeV domain, where this ambiguity between hadronic leptonic scenario is still today, I would say, very strong and not solved. So this is RX J1713.7-3946. This is a shell-like supernova remnants. So let me just try to give you an overview, even from the historical point of view. These are observations that date back to 2008. So we didn't have Fermi still operational, and there was a Hess observation, and then radio and X-ray observatories. So actually, you see that in a very, let's say, simplified leptonic model, where you have a unique population of accelerated electron, and you need to assume a kind of 15 microgauss magnetic field to reproduce this X-ray and radio observation, but then you would fail to reproduce all of the S data. And on the other hand, with the anadronic model, where you interpret the S data as a pi0 decay, you would somehow overshoot radio data, even though I have to say that these are only from a limited part of the remnant. So one of the main discriminants would have been to have Fermi data in this energy region to see the trend, if it was declining or a flat slope. Let me also mention that there have been revised model of leptonic interpretation, where apart from interaction over the CMB, you also have interaction with some enhanced optical field that could give this second bump and reproduce the S data, or with two electron population. And when actually Fermi data came, they show this actually hard trend in the GeV domain. But this was not immediately interpreted as a leptonic radiation. In fact, it was proposed another model where basically you have hadronic origin of the radiation, even with this kind of bell shape, but where basically the propagation of this, so you basically have an e to the -2 accelerated spectrum of protons at the shock of the remnant. But if the remnant is propagating not in a uniform environment, but in a somehow environment populated by clumpy material, then you would have that the interaction of the shock with these clumpy clouds, molecular clouds, these are very massive and very dense. So the passage of the shock through the cloud would not destroy them. But on the other hand, it would amplify somehow the magnetic field all around the cloud. And this would prevent the low energy protons from penetrating inside the cloud and interacting with the dense target field. So the idea is that this hardening is produced by basically diffusion properties of the protons in this very inhomogeneous environment where the shock might propagate. And this situation is quite actually is quite common in the explosion of supernovae, which are of type 2 origin, so core collapse supernova, where you had basically a massive star exploding, and before of the explosion, the red giant phase with strong wind had created a sort of environment with very dense and fragmented material all around. So we actually performed, this is a work that I did during also my PhD, some kind of detailed numerical simulation of the proton transport in such kind of environments. And I show in this slide the very result of that study, where we could reproduce actually both the GV and the TeV data with the anhedronic model that was assuming a magnetic field. Well, we saw through MHD simulation of shock interacting with dense cloud that the magnetic field all around the structure was amplified by about a factor 10 with respect to the interstellar magnetic field. So we are assuming here that basically the magnetic field around all this clamp is of the order of 100 microgauss with respect to 10, which is the standard, let's say, magnetic field in the downstream of these sources. And basically, we couldn't actually tell what is the value of magnetic field inside the cloud. So here there are two kinds of modelings done with 1 microgauss or 10 microgauss inside the cloud. But the important point is that this model could reproduce the high energy data basically with a kind of energetic in cosmic rays, which is totally comparable with what one would expect in the supernova remnant scenario for the origin of cosmic ray. This is of about 2% of energy conversion from kinetic motion to cosmic rays. Let me also say that in particular for this SNR, there are molecular and atomic gas clouds observed overlapping with the TeV morphology of the SNR. Here the TeV morphology is shown in the grayscale, while molecular clouds are CO clouds observed by the Nanten telescope, and H1 lines observed by Atke and Parkes. So these are observed actually in coincidence, you see, with the peak of the TeV emission. So there is reason to believe that there are plenty of this structure in the environment, in particular of this SNR. And another signature of the presence of this cloud has been observation actually in the X-ray domain of time variability of tiny filaments that we interpret as the molecular clouds where high energy electrons soon lose energy in the amplified magnetic field. So you see this 10 arc second, 20 arc second structure, which show variability through the years. And this is consistent actually with 100 microgauss and milligauss magnetic fields in the amplified layer of the cloud for timescale of synchrotron losses of the order of few years. So actually, as I've shown, it is not really obvious to discriminate through the radiation if protons are accelerated or mostly electrons are accelerated in these sources. And one key in discriminating these two scenarios would be to measure neutrinos from this source. This is why basically this is what the neutrino cubic kilometer scale neutrino telescope are trying to show. Basically both IceCube, which is operative in the South Pole, and KM3net that we are building in the Mediterranean Sea. And in this basically plot, it is shown the predicted neutrino flux. You should look at the dotted lines from this source, starting from the assumption that the radiation that is observed is 100% hadronic in nature. So these are somehow twin neutrinos that are twin of the gamma rays produced by pi0. You see two lines because actually the gamma ray fluxes measured by S at different years slightly differ in the cutoff, and this might be a crucial region actually for neutrino detection. And the KM3net sensitivity to mu neutrinos that emerge in the pion decay and that constitute the best channel to observe astronomical sources because they give the best angular resolution. So this shows the sensitivity of KM3net to mu neutrinos and the mu neutrino flux expected from the source. So you see that actually the presence of a cutoff might be very limiting in detecting this source, but there is an interval in energy around 10 TeV where actually some studies might be possible. And in the next year, we really wait for news on this side. Well, this is not only this is not the only interesting source, but this could at least discriminate the origin in there of the radiation. Now, let me just try to give an overview of few interesting supernova remnants as they are observed in gamma rays from multi-GeV to multi-TeVs. So the RX J1713 is the source that you see here as a dark red point. But there are many other remnants of supernova observed in gamma rays, and they all show quite different spectra. So this is somehow something that we should try to understand. Basically, none of them is showing an e⁻² power law that you would expect, for instance, in hadronic collision of e⁻² protons. And in particular, we see somehow different population of supernova remnants. We have some very young sources, let's say some 1,000 years old, like the one that I was discussing in the last 10 minutes, which show cutoff at the level of few TeV in gamma rays and hard spectra in the GeV domain. Then we have very young sources. These are few hundred years old. These are, we believe these are basically really at the stages of starting the particle acceleration. So they have quite steep spectra. And then you have the oldest system, which are also the one where the characteristic pion decay bump was claimed, like W44 and IC443. These are some 20,000 years old sources, which show a quite, I mean, if you compare, for instance, 1,000 years old with a few thousand years old SNR, you see some interesting trend. First of all, it seems that the maximum energy that this accelerator produce is evolving with time, and is in particular decreasing with time. So older systems, they basically have lower maximum energy. And also the spectrum is quite different. You see how above the maximum energy, the spectrum is quite steep. So of course, we should try to build a consistent picture of the whole of this observation. Let me also, in particular, concerning the maximum energy that the middle-age SNR are able to achieve, to show you this collection of maximum energy as a function of the age of the system, which somehow now, with great systematic uncertainty on the evaluation, in particular of the age of the system, you can see a general trend which shows that somehow the maximum energy is a decreasing function of the age. And that's something that I will discuss in the context of a model where in addition to the acceleration of the cosmic rays in these sources, we should account for how the sources are able to release the shock and be injected into the galaxy, and basically then propagate diffusively up to us and being observed as the cosmic ray spectrum shown in the first slide. So here I collect a few open questions that we are working on. First of all, if SNR might act as a PV accelerator. So do they accelerate protons, and do they do this up to PV energies? If so, are also the main contributors of the galactic cosmic rays, and how particles then escape the shock? And then we should explain the different observation of supernova remnants if this scenario is true. Why the spectra are steeper in the Middle Age system, and is it consistent with theory, the fact that maximum energy is decreasing with time? So in order to do this, I hope I convince you that we can work with the gamma rays, neutrinos. And I here include another messenger, which is hard X-ray synchrotron photons, which might be emitted by the secondary electrons produced in the muon decays. So about the issue if SNR might act as proton PeVatron, we can think of a zero-order estimation of the maximum energy that these accelerators are able to produce, and this is simply computed with an Hillas criterion, where you impose that the size of the when the Larmor radius of the accelerated particles is smaller than the size of the accelerator, and you end up in an estimation of maximum energy, which actually involves the shock speed, the shock radius, and the upstream magnetic field. So with the typical parameter of supernova remnant explosion, so like 3,000 kilometers per second of shock speed, 3 parsec in shock radius, and some 10 microgauss magnetic field, we end up in a maximum energy of accelerated protons, which is about 100 TeV. This is a bit, let's say, 1 decade below the knee energy that we need to explain the cosmic rays up to the first spectral break. And so to solve this issue, we might either assume that the PV particles are accelerated only at the initial stages of the remnant explosion, when the shock speed is increased by a factor of few. But most of the time, what is studied is the presence of amplified magnetic field as obtained by cosmic ray gradients. So the self-amplification of the magnetic field by cosmic rays. And this is needed in the upstream, as I told you before. And these are the only two scenarios that we can think to explain PV energies at supernova remnants. So if these PV particles are produced, the question is, do we expect to see them at supernova remnant, for instance, in gamma ray observations? Well, we expect that at some point these PV particles are able to escape the shock. And this is a time-dependent process and an energy-dependent process. So actually the spectrum which is accelerated at the shock is different from the spectrum of particles that escape the shock. And this is, of course, due to propagation effect in the galaxy, which depend on the diffusion coefficient, is different also from the spectrum that is then propagated in the galaxy and that we observe on Earth, that also depend on the characteristic of the telescopes. So having given this broad overview of the open question, let me just go through the plan of the talk. So I will describe you a phenomenological model that we developed to describe particle escape from Middle Age supernova remnant shock, and I will in particular describe what are the impact on the spectral signatures for gamma rays, and also show some predictions in the 100 TeV domain, which, as I will show, are crucial to discriminate if SNR have acted as PV accelerators. And then I will suggest another way to look actually for PV accelerator, which is through passive clouds that are located nearby of supernova remnants, but not embedded into the shock, so some few hundred parsec away, from which we might expect proton-proton collision to occur and then high energy radiation. So I will show also some comparison of this modeling, which is based, of course, on the escape of cosmic rays from the sources with the S-galactic plane survey. So I will ask if you have any question on this initial part of the talk, something which is not clear.
So Silvia, I have one general question. So out of curiosity, we only have a handful of supernova remnants for which we have some evidence for the pion bump, right?
Exactly.
And my question is this an instrument problem, or is this reflecting some underlying properties of the supernova remnants?
No, I guess, well, let me say that the pion bump has this exact shape, let's say this flattening, only if you have an accelerated protons, which is e to the -2 power law. So one question in principle is if the shock acceleration spectrum is different from this e to the -2. And for instance, including the back reaction of the cosmic rays, so the self-generation of magnetic field of the cosmic rays inside the dynamic evolution of the shock, you end up in a different answer. So this is something that I guess is still not clear. And the other point, that I think it's more, yeah, of course, there are also instrumental effects, I guess, due to the energy measurement. But I would say that that this is mostly due to the acceleration spectrum.
I see. So let me see if I get it correctly. So the bump appears only. The bump appears clearly only in the idealized case where you have
this shape, actually, this shape which is flattened. Right. Okay. Otherwise, it reflects somehow also the spectrum of the primaries.
Yeah. And it's more difficult to identify. Yeah. Yeah. Of course.
I mean, it is more difficult because it is actually degenerate with what you would see with the electronic scenarios. That's the issue. And as I've shown for the first SNR, the RX J1713, you don't see at all the bump, even though you have an e to the -2 for accelerated protons and the hadronic interpretation for radiation, because you are propagating into a non-uniform environment. So this is also very important. I mean, detailed modeling of how the particles propagate is crucial to infer the secondary radiation.
Right.
Okay.
Right. If you have any other question, just unmute yourself. Don't see any, so I think, Silvia, we can just go on for now.
Okay, so let me first jump to the first item of the talk. So how particle escape. In particular, I will just show a model for middle-age SNR, even though we are extending this model for young supernova remnant too, and this will soon be published. But for now, we'll focus on middle-age sources. So we want to answer the question how the accelerated particles become the cosmic ray observed on Earth. So of course, the process of escape has impact not only on the cosmic ray flux, but also on the spectra of supernova remnant, because to some extent, we expect to see the radiation from supernova remnant coming, for instance, from accelerated protons that are somehow still located in the region of the SNR, okay? Those that have already left the remnant are more likely, and these are the most energetic ones, are actually more likely to be found displaced from the SNR itself. So I will show you a phenomenological model that will be able to describe SNR spectra. But before doing this, I have to give you an introduction of how an SNR shock evolves with time. And this is basically distinguished in several stages that I enumerated here. So first of all, the shock expanded almost constant speed because the ejecta mass of the star is much higher than the mass that the shock continuously accumulates while expanding. And so basically, this is the so-called free expansion stage or ejecta-dominated stage. Then at some point, the mass that the shock is accumulating starts to be comparable to the ejecta mass. And so the shock somehow feels the inertia of the accumulated mass. And then we move to the set of Taylor stage. And in the passages between these two stages, as I will show, we expect basically the escape of cosmic ray to start. Okay, so basically the first stage is where acceleration occurs, and the second stage is where cosmic rays low energy are still confined while the highest energy start to escape. Well, in the latest evolution of the remnant, radiative losses start to be relevant, and later on, basically the pressure of the expanding mediums becomes comparable to the pressure in the ISM, and the remnant stops its expansion, basically. So this is another way of seeing these different stages of evolution. So this shows the radius of the blast wave with respect to time. So we start in the free expansion where shock speed is almost constant and the shock radius increases linearly with time. Then the shock speed basically decreases entering the set of stage, and also so the rate of expansion basically decreases. And then the time dependence of shock radius becomes less relevant until basically the shock radius becomes constant and the merging is complete with the ISM. Now, we should understand how the maximum energy of accelerated particle evolves through these several stages. And a very easy analytic estimation could be done by assuming that the acceleration of particle is limited by the age of the system. So if you write down basically a few equations, you end up that the maximum momentum of the particles that's produced at the shock is directly proportional to the shock speed squared the time and the energy density in magnetic fields, okay? Because this affects the acceleration time that's scaled as the diffusion coefficient, the effective diffusion coefficient. So basically, during the free expansion stage, you have a constant shock speed, and you expect this dependence of the maximum momentum over time. During the set of Taylor stage, you have decreasing shock speed with time, and so you expect this other trend. The important point you should focus is this time dependence on the time evolution of the magnetic turbulence, okay, this F of T. So if one was able to perfectly understand how the magnetic field, and in particular the turbulent component, evolves in the environment of the SNR, then I mean you would be able to clearly have a receipt for how the maximum momentum of particle evolve with time. That's something that we decided to treat somehow phenomenologically. So we parameterize the maximum momentum as a function of time, as a power law in time, a decreasing function of time with the slope delta. And we want to try to understand if gamma ray observations are able or not to suggest some realistic values for this delta index. So after the start of the set of time, we basically write down this parameterization. So we assume that at the set of time, you achieve a maximum momentum Pm, which we take to be for the next slides as a PeV. So we assume that SNR acts as a PeVatron, and then the maximum momentum starts to decrease with time during the set of stage with this slope. And inverting this relation, you can infer what is the time of escape of particle with the momentum P. So basically, you see that the highest energy particle from this relation are expected to escape earlier than the low energy one. And of course, the set of time is something that depends on the physics of the explosion, so on the supernova energy, the ejecta mass, and the density. We assume this modeling for a uniform density medium and 10 solar mass of ejecta. So this ends up in some 1,000 years old set of time. It means that, for instance, the RX J1713, which has almost this age, is at the stage of moving to the set of phase. So it's really accelerating now the highest energy particles, and these are starting their escape. While the middle-age sources, of course, the highest energy particles have accelerated some 10,000 years before, even more. So let me just give you an idea of what is the value of this index delta according to theory. If we had no magnetic field amplification during the set of stage, this delta index should be of the order of 1/5. So this comes from the previous slides. Well, if the magnetic field, turbulent magnetic field, is amplified by resonant interaction of cosmic rays, then you expect a value of 7/5. And then in the end, if non-resonant waves are somehow amplifying magnetic field, then you expect a value which is of the order of 2. So you see that inferring the value of this delta can also drive us toward the physical mechanism that is possibly producing the amplified magnetic field that is responsible for the PeV energies. So with this receipt for how particles leave the shock, we started the solution of the transport equation of the cosmic rays. So this equation describes the temporal space and energy evolution of the particle density, this function f, in the shock, basically velocity field, and including the adiabatic energy losses and the cosmic ray diffusion, of course. And we try to implement an analytical solution of this equation by accounting for the spatial profile or velocity profile of the plasma downstream of the shock, and basically separating the cosmic ray distribution function into two populations. So confined particles inside the SNR are basically particles that are really attached to the shock. They have a momentum which is smaller than the maximum momentum that the shock is able to accelerate. While on the other hand, you have escape particles which have a momentum which is higher than the maximum that the shock can confine, basically. And so once these particles are considered as escape, they are subject only to pure diffusion in the magnetic field of the remnant. And of course, the two distribution functions are linked together, because the particles that were confined at the escape time are the same that will start escaping at the same time. Okay, so we solved these two equations somehow coupled and analytically. And I mean, if you go to the paper, you find the analytical solution, which is obtained under a few assumptions. First of all, we try to simplify the description by assuming a spherical symmetry. Of course, this is not necessarily the case, but this is what will be considered in the following. And then we assume that the diffusion coefficient is uniform in space and also is constant in time. And we take a momentum dependence of the order of 0.3 and a normalization that we leave free to vary in order to describe the spectra, as I will show you, of supernova remnant, the gamma ray spectra emerging from PP collision. So another important assumption is about the acceleration efficiency. So we assume that at every time, a constant fraction of the ramp pressure, rho v square, is converted into cosmic rays. And we assume a pure power law as p to the minus 4. And we only take evolution for the dynamical variables of the SNR shock following the set of solution. So this is a description of basically what happens to the distribution function of escaped cosmic rays as a function of the radius. So of course we we obtain this analytical solution all over the remnant, all inside the remnant, and we can predict also how the cosmic ray propagate outside. So you see here that basically with the p to the minus 4 power law in accelerated particles, the spatial distribution of the escaped cosmic rays is basically flat inside the escape radius. And after the escape time, you see the different colors. This distribution starts to smooth out, of course, because diffusion starts to be effective. And this is shown at different energies of cosmic rays. So, of course, it depends on, so the highest energy you see, there will be a fixing time, a minor fraction of particles inside of the SNR. But still, we are able also to describe the presence of escape particle at times later than the escape time inside the SNR itself. So we can compute, for instance, the integrated spectrum over the shock of the SNR of protons located inside the shock. And this would be, this is shown for different values of the index delta. So for instance, let's focus on one individual line among these. So you have this contribution from the confined protons. You see the simple injected acceleration spectrum. And then you have basically that also escaped protons are still propagating inside the SNR. So they enter in this integration and they give this kind of contribution, which instead is decreasing with the momentum. But at the highest energy, you also have the particles that are escaping from the acceleration region, which is the precursor. So you have this kind of flattened trend. And if you look, for instance, at the spectrum of protons you would expect from an annular region all around the SNR, I mean, you basically integrate from the radius of the SNR to, this is shown for solid line twice the radius of the SNR, then this is the result that you would get. I mean, only the escaped particles, of course, are located outside of the SNR shock. And so you see this kind of quite peculiar trend with a low energy cutoff in the proton distribution, because the low energy cosmic rays at the time where this spectrum is computed, which is at about 10 to 4 years, didn't escape yet the shock. So they cannot be found outside. So this means that you also have, of course, escaped protons both inside and outside, and so you might, for instance, want to compute the result of PP collisions with the target gas in this region. We assume the set of profile of density inside the SNR. You see here the compression ratio at the shock radius with an upstream density of 1 particle per cubic centimeter. And these are the resulting gamma ray spectra. For instance, this is inside of the SNR for different value you see of delta. And this is in the same annular region shown before outside of the SNR. So, of course, let me first discuss what is shown outside. The sharp cutoff that was seen before in proton is now much more smoothed in gamma rays, but you see basically a peaked distribution where the peak is basically corresponding to the maximum energy that the shock is able to confine at the age of the observation. And if you look at inside, you see again a contribution. Here you have the dashed from the confined proton and the should be dotted from the escaped protons. So you have escaped protons. I mean, they have formally escaped the shock, but are still propagating inside the SNR. And so you have a contribution in gamma ray emission even from those particles that again show a similar trend as the one that could be found only outside. And so we tried to model for instance, the observation of several supernova remnant like IC443, W51, and W28 with this model. So, for instance, if you look at IC443, you see that a p to the minus 4 power law in protons is able, this is the acceleration spectrum, to reproduce this gamma ray emission as hadronic in nature if you assume either that the delta index is 3, this index that defines the energy dependence of escape time, and that particles were accelerated at set of time up to 1 PeV, or there is a sort of degenerate solution with delta equal to and P max equal to 100 TeV. So this case would not configure SNR as PeVatrons. So you see that it is extremely important to have 100 TeV measurement to understand how the spectrum is basically the gamma ray emission is going further in energy. And let me also mention that in all these modelings, the kind of cosmic ray energy that needs to be converted, the supernova energy that needs to be converted to cosmic rays is between 2 and 15%. So again, quite compatible with what is typically assumed. And the important point is that you need basically to reduce the diffusion coefficient in the region all around the SNR in order to reproduce with this kind of parameters the gamma ray spectra. So this gives somehow an indication that actually if the diffusion coefficient is suppressed with respect to the average galactic value, then we should also be able with the next generation instrument to observe some kind of halos of escaping cosmic rays all around these sources. Let me also mention that all these modelings, as you see, indicate that delta is 2, 3, sometimes even 4 in other sources that are not showing here. So this of course, give us an indication of the fact that I showed you before the reasonable values of delta according to theory. So perhaps beside the magnetic field amplification, also damping effect might be relevant to increase this delta to the value pointed by the observation. So clearly, these are very interesting aspects that the next generation instrument, in particular in gamma rays, might explore. Let me now go briefly, as I'm actually out of time, to the second part of the talk. I will actually suggest you to have a read to a paper that we published, is referred to in the next slides, very recently. So the idea that the protons that are escaping, well, they might be somehow, they might be propagating close to the source in the very beginning stages of the escape, no? Because they found a region with increased turbulence, but then at some point they might escape totally the region of the SNR and meet nearby clouds where proton-proton collision are likely to occur. And so from the resulting gamma rays and neutrinos, we might be able to study the same PeV cosmic ray accelerated in supernova remnants, but somehow displaced from the position of the SNR. And this also, let's say, is consistent with the fact, I would say, that HESS, which is so far, I would say, one of the most sensitive imaging atmospheric Cherenkov telescope for the observation of TeV gamma rays, is showing many unidentified sources in the galactic plane. This might be really these molecular clouds that are actually not active sources, but passive target for for accelerated protons. So we actually tried to build somehow some catalogs pairing the known SNR as observed and cataloged in the green list with the observation of diffuse molecular clouds given by the RICE catalog, which is a survey in CO. And basically, well, one of the, so we tried to understand which cloud is located in proximity of SNR, and which of them should give a detectable signal from a gamma ray instrument. And well, of course, the most difficult part of this game is the knowledge of the SNR distance, because only for 60% of the green catalog, this is a quantity which is known, while the RISE cloud catalog gives distance for all of the clouds. So we need to assume that if the SNR distance is known, a pair is found between SNR and the cloud if they are located along the line of sight within 20% of the SNR distance, or within 100 parsec from each other. But if the SNR is not known, then we assume that the SNR is located at the same distance of the cloud. And of course, this gives somehow a conservative estimate, somehow an upper value for the expected gamma ray flux from these sources. As in fact, I mean, the SNR sometimes is assigned at two different distances according to the cloud that it is paired. So of course, in reality, the SNR is either close to one cloud or to the other. And so really this should be regarded as somehow upper limit. So in this next slide, I show a survey of the galactic plane as obtained by Hess in 2,700 hours of observation. And you see, this is covering basically galactic longitude from, if I remember correctly, 260 degrees to 60 degrees. So with the galactic center included. So you see the S identified the sources as contour. You have the triangles where the source is located, and then green, black, and cyan contour. Basically, the green are 5 sigma detection, 5 sigma contour. The black is 3 sigma contour, and the cyan, which are here somewhere, are 15 sigma contour. And the color scale instead shows, well, the dot show the position of the cloud that we coupled to SNR, and the predicted integrated gamma ray flux above 10 TeV, assuming this value for diffusion coefficient, which is the quite standard in the ISM, and the index delta equal to 2.5 for the escape of the protons. So we basically make the propagation from the location of the SNR to the location of the cloud, assuming in case also the age is not known, assuming it's evolution with the set of parameters. And okay, what you can, the take-home message from this study, I mean, I could discuss a bit the many sources that are here identified. For instance, in this case, there is this Hess sources, which is an 9ID source that is overlapping actually with the one bright cloud. So the two might be connected. In other cases, the predictions, for instance, let me go very rapidly here. Are, for instance, these two clouds have predicted fluxes which are not, first of all, here you don't see actually the background SNR. I just write in few locations where are they interesting, but if you go through the paper, you can find it all detailed list of these pairings. But for instance, in this case, there are two clouds that are above the Hess upper limit. So these are not detected by us, but would be predicted by our model. And it means that the SNR that was associated to the cloud, which is the J1713.7 plus 0.4, is not located at the location of the clouds. Okay, so, well, I suggest you to have a look at the paper because there are very interesting regions. Unfortunately, let me say that here in this slide, where the galactic center region is located, the RISE catalog do not provide information. So this region is excluded, but there are many other interesting regions like the Westerlund 1 and the Westerlund 2 complex, which are massive also stellar cluster. where PV particles are also believed to be accelerated. And there might be, for instance, this is the Westerlund 1 complex, and there is one SNR in this complex that might power up part of the gamma ray emission that is observed in this region. So, of course, let me jump to some predictions also for CDA. There are some 20 pairs of SNR cloud that are expected to be visible by CDA above 100 TeV. This is a sort of parameter space with the integrated gamma ray flux above 10 TeV, where the color are systems that are expected to be observed by CDA. This is above 10 TeV, yes. And this is, for instance, a table that shows which are the median properties that one would expect to detect from the median properties of the cloud and the SNR system that one would expect that they would be detectable by CDA again. So you see, for instance, that the preferred systems are those with quite dense and massive clouds, so 40 proton per cubic centimeter, some 2 to 10 to 5 solar mass with radius of the order of 30 parsec, and was a distance from Earth 4.5 kiloparsec, and with SNR age of the order of 21 kilo year. This is to allow actually particle escape to and the highest energy protons to reach the distance, the 30 characteristic parsec distance between the SNR and the cloud. So let me just conclude by saying that so far we don't have confirmation of PV accelerator. There was a suggestion of a PV accelerator in the galactic center that, however, is very much debated. And of course, the observation above 10 TeV up to 100 TeV and above are very crucial to understand the presence of PeV protons. Let me also say that I didn't go through this in the talk, but clearly sources other than SNR might contribute to the galactic cosmic rays. And for instance, the massive stellar cluster that I mentioned in the also HESS galactic plane survey might play part of the game. What we need to do is really combine different diagnostic, like the high energy radiation, both spectroscopically and morphologically, but also neutrinos, also synchronous radiation, and also really radio map of gas distribution. And here I wanted just to suggest two possible strategies to look for these PeVatrons, like looking for TeV halos around SNR, and also using passive interstellar clouds as illuminated by nearby SNR. And clearly, we hope that the future observatories will shed light on these very important issues. Okay, so this is all from my side, and I'm sorry for being late. Just go for questions, please.
Thank you, Silvia. It was a very nice review and interesting results. So I don't see any hands raised yet, but I have one question. Maybe we have time for 2 or 3. In your slide 40, you were showing the values that could explain hadronic acceleration from these 3 SNRs.
Yes.
So my question is, are these values that you show on the right, are these from a fit? Or something that you manually found that works?
No, this is, I mean, this is not actually a fit. Let's say that what mostly, so we started from, for instance, SNR ages and density as estimated in the literature, also distance, of course. Then we went with our cosmic ray simulation with P⁻⁴ power law and fixing the maximum momentum. And then we explored a little bit, for instance, what is the value of the cosmic ray acceleration, which is needed to reproduce the level of the gamma ray emission. Okay, but the other values are actually taken from the literature. So this is one of the parameters, and the other very important is the the value of the diffusion coefficient, because of course this will somehow relate to the amount of time that the particles are spending inside the SNR. So the spectra are obtained integrating, of course, in the shell of the SNR. So you need to know somehow what is the diffusion coefficient in there to find out how many high energy particles will be there at 15,000 years old, okay?
Right. So regarding what you just said, so one thing that would be interesting for me would be to see like a comparison between an actual fit for a hadronic model, your model, and a leptonic model, and see some kind of like a model preference or something like that would point to hadronic being more.
Okay, let me say I fully agree with this, and in fact we are so we are working to extending this model for electrons, so the accelerated and escaping eventually electrons from SNR, because this is what would give us the chance to understand the leptonic predictions. This is not, let's say, with respect to the model that I presented, this is an analytical model, okay? So this is not including, for instance, the energy losses of protons, because these are let's say, we just included the adiabatic expansion losses, but not because of radiation, okay? Because this is typically not relevant for protons, but it is for electrons, at least the synchrotron radiation in the magnetic field, the self-amplified magnetic field, and inverse Compton. So we are working at this description numerically, and actually, we have a paper ready for the electrons and the comparison with the cosmic ray electron spectrum observed on Earth. And we are also working at this supernova remnant application. So I will point you to the paper once it is out.
Yes. Do we have any other question in the audience?
I have just a curiosity.
Yes.
So thanks for the nice talk, Silvia, first of all. And second, the question. So you were showing us the map where with the several supernova remnants in very messy environments close to other sources such as star clusters or some other, I don't know, whatever, the central molecular zone or other objects. So my question is there a way, maybe a multi-wavelength description that might tell us clearly or with a better constraint if supernova remnants are actually accelerating the particle produced in the gamma ray spectrum we observe in these clouds? So can you envision any possible signature of the origin of?
Well, this is a difficult question because, yeah, I mean, I think the best way is really to go with this multi-messenger and multi-wavelength constraint, because at least, yeah, if you observe, I don't know, as we suggest in this work, the radio so the presence of molecular clouds from radio, and then you have a consistent, let's say, observation of SNR nearby or of stellar cluster nearby, and then you have this some model which tells you also how the time dependence emission of this the time dependence of this emission should be. Then I guess it would be a more stringent conclusion. One of the things that we also suggested, and yeah, we plan to better investigate it in a future work, is as a counterpart of the hadronic gamma ray emission, the emission from secondary electrons, okay, because I didn't go through it. But of course, if you have molecular clouds that are sufficiently far away from the accelerator, sufficiently far away means that the electrons, the primary electrons that are accelerated in the shock region would not be able, because of energy losses, in particular the synchrotron in the downstream and so on and so forth, would not be able to reach the target cloud. So in principle, you could see the synchrotron radiation only from the secondary electrons that are produced in the PP collision in the cloud. So you should also be able to see this cloud somehow brightening in X-rays, because if the PeV protons get there, then of course you have the 50 TeV electrons radiating. And so you might somehow, knowing by other methods the magnetic field of the cloud, which is also something that is given. I mean, it's not of course very easy, but for instance, you could use the Zeeman splitting effect to estimate it. And then you might have a model that is able also to describe the spectrum, the multi-wavelength spectrum. And I guess this might be somehow crucial to really understand the spectrum of accelerated particles. But I guess it would not be super easy, I mean, to distinguish if the particles were accelerated in an SNR or, I don't know, at the termination shock of a massive stellar cluster.
Thanks. No, I was thinking maybe some possible halos due to leptonic emission in the supernova remnant surrounding or things like this. But I'm not an expert, so I can't envision how would be, I don't know, the time scale of inverse Compton on the CMB for these electrons propagating from the shock of the SNR to the cloud or so.
Well, I mean, the issues that with the electrons in SNR is that really you don't really expect to have this TeV leptonic halo because of the huge energy losses in the. So let me put it like this: if the SNR are accelerating protons up to the PeV, then these protons might really, you expect highly amplified magnetic field to produce this PeV protons. And the electron losses in this high magnetic field would be very stringent. So I would not really expect to have halos of electrons around these sources, at least SNR.
Okay, thanks.
All right. Thank you again, Silvia. This was wonderful. I'll have probably a couple questions for you offline, because you got me interested in this, and I'll email you the link to see your video later. Thanks everyone for being here, and remember we have a special. Well, we'll send out the announcement for a special Astroparticle seminar next week. Thanks again, Silvia.
Thank you very much. Thank you. Bye.
Bye bye.
Thank you.
Bye all.